Hello, everyone, and welcome to my presentation about large language models and OpenAI API. So throughout this talk, I'm going to overview some key concepts related to LLMs and also use OpenAI API to provide key examples or practical examples. So, and particularly, I will dive into some key concepts for any user of LLMs. So particularly, I'm going to talk about the language objective, language modeling objective, architectures, decoding strategy of LLMs, types of LLMs, what does it mean in context learning, fine-tuning, LLMs use cases, and the generative AI lifecycle. And also, I'm going to highlight the chat completion API endpoint, fine-tuning API endpoint, and embedding API endpoint from OpenAI. Okay, so let's start with this technical and strong definition about LLMs. Typically, large language models refer to transformer language models. So here we have two key concepts, transformer and language model, that contain hundreds of billions or more of parameters, which are trained on massive text data, such as GPT-3, Galactic Pencil. LLMs exhibit strong abilities or capacities to understand natural language and solve complex tasks like translation and so on. And all this via text generation paradigm. So this definition covers mainly the key concepts about LLMs. LLMs are large language models, and language modeling is one of the main approaches, the major approaches used for natural language understanding and generation. So technically, language modeling objective aims at modeling the probability or the likelihood over a corpus, so to predict the next word or the future word or the missing words. Okay, LLMs are language models, but based on the transformer. So here we talk about the architecture of these language models. So transformer is a deep learning model. So it contains many, or the main component of this deep learning model is the attention mechanism. So this deep learning model contains many layers of deep attention stacked deeply in a neural network. So the original transformer model describing attention is all you need, proposed by Buzz 1 year old from Google in 2017, contains two parts, the encoder part and the decoder part. And it was designed for translation task from a language to another. But LLMs, or currently, LLMs are mostly built upon the decoder part and not the encoder. So one interesting property of transformer is that it processes the textual data or data in general in parallel way, so which deals with the records that we had before in LLMs. Okay, so the next key concept is scaling. So LLMs contain hundreds of billions of parameters which are trained on massive text data. So this is related to scaling technique. Scaling is one of the techniques that leads to the success of LLM, and it is one of the main findings at early stage of LLMs. So here you can see, for example, The model parameter size of GPT-3 is 175 billion. It is approximately twice of the neuron in our brain. And the pre-trained data scale, for example, for Palm, released on 2022 was 780 billion tokens. So we have models with big size in parameters and also in training data set. Okay, so LLMs exhibit strong capacities to understand natural language and solve complex tasks via text generation, which means that we approach many NLP subtasks using text generation. We approach classification problem, clustering, summarization task, spell checking task, translation task, using just the main objective function, the main approach. Generate, given a sentence, generate the next one. Okay, so this is an example of a prompt that we gave to GPT 3.5. So it is a prompt about spell checking task. So we have here a good completion, good response, and also an NLP translation task. So which means that LLMs are task agnostic models. They don't depend on the task itself. Okay, so they are not a task specific. So before we train a model or maybe a machine learning model or deep learning model for one task. But here, those models can handle many tasks at once. Okay, this is just the timeline about of existing language models, larger than 10 billions of parameters. So you can see here that the leaders of IT have developed and released LLMs. So we started on 2018, 2019, and within 4 years, there are now hundreds of LLMs. So we have publicly available LLMs and closed LLMs like GPT-4, GPT-3, and so on. This table shows some statistics of large language models. You can see here, for example, so the size of parameters and the pre-trained data scale. But what is important here in this table is the scaling laws for LLM. So we have now a scaling law about LLM, about the size of parameters and also the size of data set. So which means, so if we take, for example, the chinchilla scaling law, so proposed by Google DeepMind, the team on 2022. So chinchilla scaling law argues that the scaling of size, data set size, and also on parameters should be scaled at equal or should be increased at equal scale. This is also a good finding about LLMs. Okay, so this slide summarizes the major development stage of language modeling approach. So we start with statistical language modeling based on Markov assumption, then neural language models, like so based on NLM. Work today is just a shallow neural network on 20 or developed proposal 2013. Then pre-trained language models like LMO based on LSTM by LSTM, BERT based on transformer architecture, and then now the large language models is the term coined to large size pre-trained language models. So what is important for the LLMs is that the emergent abilities. So emergent abilities like in-context learning, instruction following, so described by the colleague Najib, step-by-step reasoning. All those abilities or those capacities are emerged as a result after pre-training. Our LLM isn't trained on these abilities, but they are emergent abilities that we can deduce after pre-training. So I'm going to explain this in detail. Okay, so I said before that the LLMs approach all the natural language processing tasks as text generation. So you can see here, so this is the dynamic animation. So if we give here an input inside the first law, the GPT or an LLM can predict the next word. So I'm here another figure is this one. So here this is the general, or this figure shows the general working flow of an LLM predicting the next word called autoregressive model or causal language modeling. So here, at the first step, suppose that we have the generative artificial intelligence and I reference to. This is my input. So the LLM will predict the next word, so the next word over the whole vocabulary of this LLM. So each LLM has a vocab, and the next word will be predicted from this vocab. And it will be here, so a probability will be assigned or affected or computed by the LLM to each word. Then we select the next word. So we append this next word to the original input, and then the LLM predict the next word, and so on. So at the end, the LLM is focused on generating the next token given the sequence of tokens, and it does this in a loop, appending the predicted token to the input sequence. And with this way, we can generate text. That's why LLMs are considered a good example of artificial generative artificial intelligence. Okay, let's go deeply or dive into the details of this text generation. So here, my LLM compute the normalized log probabilities first, and then it selects the most probably word that can appears that can appear after. So here, this probability or the logits of those words, of those tokens. So here I use the word, those two words, word or token interchangeably, but LLMs works with tokens and not words. Okay, so the probability of observing a token K given the context, so given the previous words, is computed with softmax of logit and so on. So here we have the probability of each word, and our LLM will select the word with the highest probability. For now, I'm going to explain how can we also select efficiently the next word. Okay, so how to select the output tokens, also known as the coding strategy used for an LLM. So we have greedy search. With greedy search, the LLM selects the word with the highest probability. So we can model this, formally model this selection by the argmax of probability of X of observing the next word given the previous words. So selecting the word with the highest probability isn't a good choice for all NLP subtasks. Maybe it works well for example, text summarization, for translation. But for open-ended writing, like, for example, story writing, selecting the highest or the word with the highest probability doesn't work perfectly. And in this case, we have another decoding strategy called random sampling. So we sample sampling-based methods. We can sample from many words, from a set of words that have the highest probability. And the first one is called temperature sampling. So temperature sampling strategy provides a temperature coefficient that we use here. We add it to the exponential or to the softmax function. So suppose that this is the original distribution of probabilities from the LLM, so the unnormalized log probabilities or the logits. So if we decrease the temperature, this distribution will be changed and will be more narrow, which means that our model will be less random. However, if we increase the temperature, this distribution will be changed to a broader distribution, and then our model will be more random. This is very good for example, open-ended writing, story writing, and so on. Another decoding strategy is top-K sampling. So top-K sampling truncates the tokens with lower probabilities and keeps just the only samples from the tokens with the top-K highest probability. For example, here, if K equals 3, so my LLM will sample just from the 3 words, the 3 tokens, and so on. So consider only the top 3 tokens and ignore all the other ones, and sample just from those 3 tokens. So another decoding strategy called top P. So instead of selecting from the top K, so we can use the smallest set having a cumulative probability above P. So like in this case, I'm going, or the LLM will select from the words that have a cumulative probability of up to 15. So we consider only this set and then sample from this set instead of sampling from the whole vocabulary. Okay, so till now, I can draw a figure that shows the LLM as a black box. An LLM can be prompted with an input, and then it returns a completion, but it can be controlled by some LLM parameters like temperature, top P, and so on, at inference time. So let's take an example of these parameters. So OpenAI API parameter name that you can experiment on the playground is a web application developed and provided by OpenAI. So you have here the temperature, you have the top P, and you have also another parameters, presence penalty, presence and frequency penalty, load its bias in order to personalize or to customize the selection of the decoding strategy. And all those parameters can be set here at ease in a code. Okay, when you select a model, for example, GPT 3.5 Turbo, and you give here a prompt. So this is the prompt. A transformer model is A with these parameters. My model can give good results. Okay. OpenAI has released many OpenAI text generation models. So we have here the newest model, GPT-4, GPT-4 Turbo, 3.5, and so on. And we have also other models that are considered now legacy or deprecated. Okay, so we suffer from this fast-moving area about LLMs. Okay, so I have written a code, or I wrote a code just 2 months ago, and now I'm going to update my code because the API has been changed. Okay. OpenAI chat completion API endpoint. So this API is or allows you to interact with the cloud LLMs. So OpenAI LLMs are now cloud LLMs, and if you want to interact with, you should use the OpenAI chat completion API. So you have here your application. So this application should send an API request. So this is just a RESTful web services with a request with post to this URL. And the models will return the prompt as a chat completion object or a string sequence of chat completion objects if you want to mimic the chat GPT working. So typically your prompt should be formatted as follows with the system message, user messages and assistant messages. So this is a code for sending a request to the GPT 3.5 Turbo. My message is here as the system, user, and assistant, and the control parameters. So let's take a look about this type of messages. So system message, user message, and assistant message allow you to create your prompt. That's it. So our prompt using, when we use OpenAI chat completion API, our prompt should be formatted as follows. So the system message contains a high-level instruction. Okay, in order not to repeat, for example, the instruction in the data, and the user message contains the main input. For example, if I want to translate from a language to another, so my sentence is the user consent. And if you want to create a multi-turn conversation between users and the assistant, you can add a role user assistant and so on. Let's take an example in order to get a first understanding about this. So this is a chat completion request. So the simplicity of OpenAI is very surprising. So you can send, as you can see here, a prompt by just these lines. So, using completion or the method create of the object completion, you can choose your model. You can hear the, for example, role message. You are a helpful assistant. You will be provided with a general knowledge question, and your task is to provide a concise answer. So this is the system message. As you can see, is a high-level instruction. And the role user, so here I give just the data, mean who won the World Series in 2020. And then, so set all those parameters. This is the chat completion API response. As you can see here is JSON object with the main message. This is the completion role assistant, and the completion is the Los Angeles Dodgers and so on and so on. And many other information about this completion, like the used model or the model that is used, the object is just chat completion, and some statistics about the completion tokens, prompt tokens, and total tokens. Why? Because it is a paid service. It isn't free. Okay. Okay. So having now this first understanding about LLMs, let's move to the pre-training of LLMs. So it is an supervised pre-training task, as it is said by my colleague Abdul Majid before. And the language modeling task is as follows, can be modeled by this probability, by this likelihood. As you can see here, so the language modeling task is the most commonly used objective to pre-train the code of only LLMs, because we said before that most, or currently the most LLMs are developed or are created from the encoder part. So given a sequence of tokens, X, X, Y. So this is the corpus of training. And then, so the LLM or the language modeling task aims to auto-regressively predict the target tokens Xi based on the preceding tokens in sequence. This is the general pre-training task. As you can see here, we train our model on just this language modeling task, and not on translation or on maybe spell checking and classification and so on. Okay, so all the NLP subtasks that you know are approached now with an LLM using this text generation likelihood. So after pre-training, with this language modeling task, an LLM is able to provide a global understanding of the language it is trained on. It is very important. And then LLMs can perform hundreds of NLP tasks they weren't trained on, or they weren't trained for. Let's take an example in order to understand what I mean by this strong sentences. This is the playground that you can use. It is free web application provided by OpenAI in order to engineer your prompt and optimize it. Okay, so the example that I take here is brand monitoring. Keep a close eye on your brand's reputation. So here, for example, we say that maybe a user, okay, so or write a review about products and so on, and maybe charged with this application, with this brand monitoring, I can maybe think to develop a similar application. So here, this is my prompt, okay? This is my prompt, formatted as system message and user message. And this one is the assistant, is the response given by or returned by the API assistant. So you will be provided by a review. And your task is to identify the following items from it. First, sentiment, it is positive or negative. Second, is the reviewer expressing anger? This is emotion recognition task. The first one is sentiment analysis task. And then another task, item purchased by reviewer, company that made the item purchased, and also the company that made this item. Format your response as a JSON object with sentiment, anger, item, and brand as the keys. So the response is very surprising. Sentiment negative, and it is negative. Anger false. So we don't express here anger as emotion. And Samsung Galaxy as the item, and the brand is Samsung. So here our LLM performs 3 NLP subtasks at once: sentiment analysis, emotion recognition, and entity extraction. It is very, very surprising. Okay. Using this playground web application, you can set those parameters. So P, frequency penalty, presence penalty, and temperature, and you can choose what model you want to use, the max length, and the stop sequences. Our LLM will generate the completion text after text. So when it should be stopped, you can give here the stop sequences, or you can also set the maximum length. Okay, those are just ratio of various data sources in the pre-training data for existing LLM. You can see here, for example, that T5 is trained on completely 100% web pages. Maybe this one, Alpha code, is trained using conversation data, okay, and so on. Okay. Types of large language models. So my colleague Abdul Majid has talked about this. I will just add some some examples. So there are mainly 3 types of LLMs. Base LLMs, so the pre-trained model checkpoints that you have just after pre-training with language modeling task. This is the first one, the base LLM. And these base LLMs have some general abilities for solving various tasks, but it doesn't consider human values or preferences. So they are not aligned, as my colleague said before. Fine-tuned LLMs, so they are adapted pre-trained LLMs for instruction, or some aligned with instruction alignment of instruction alignment, and also reinforcement learning from human feedback. And also we have another type, specialized LLMs, so specific to some domains like healthcare, finance, and so on. So this figure from Life Architecture, Architect.ai, shows the GPT-3 as a base LLM, Instruct GPT as the fine-tuned LLM based on GPT-3, so using the reinforcement learning from human feedback, and ChatGPT that we use now, it is a fine-tuned model of Instruct GPT, which is a fine-tuned model of OpenAI. So here we have used the reinforcement learning from the bug and also add some safety guards. Okay, now LLM utilization, how to work with large language models. Let's demystify some concepts. So the prompt that, or the input that you give to your LLM is called prompt. So it involves just instruction and the context. And the output is called completion in the vocabulary of LLM. So prompt engineering is the practice of developing and optimizing prompts or efficient prompts for using LLM. That is why prompt engineering is now currently is a skill in demand. Okay, so enterprise and companies research for or so have a great need about prompt engineering skilled engineers. Okay, because it is a skill in demand, let's demystify what kind of prompt you can optimize, you can write. So we have mainly 3 types of prompts: 0-shot prompt, 1-shot, few shots. And those prompts are proposed in filling the original GPT paper as in-context learning. So we have also chain of thought prompts. So a prompt where we can add some arrays on it, and it is also a sub-kind of in-context learning. Okay, so what is 0-shot? Just here, as explained in the original paper, a 0-shot prompt contains or involves the instruction translate English to French, and then you give your input without any example. So shot means examples of demonstration. So 1-shot involves the instruction and also one example of this task, like here. See author and Luther the mayor is the translation. So from this example, my LLM can give a good completion done without example. In some cases, that can generalize. And few shots involves the instruction plus many examples. Okay, and this mainly depends, for example, in the original paper, the number of examples that were used in the evaluation ranges between 10 examples and 100 examples. But don't worry about that, because the application that you want, or the application that you will use in order to send your prompt with sample 10, 20, and 100 examples automatically from your demonstrations. Okay. Let's take an example here. This is a 0-shot prompt. Classify the sentiment of the following tweet as negative, positive, neutral. I love this galaxy sentiment positive. This is 0-shot. 0-shot prompt here with emotion recognition, determine whether each item in the following list of emotions is conveyed in the text below, which is delimited with triple backticks given and so on. So here I give my sentence and then the conclusion follows. Okay, it is emotion recognition task. And you can also give this prompt in your using the playground. 1-shot prompt. So here I have the instruction, task description, and then tweet, I love the new Samsung Galaxy, sentiment positive. This is one example. And then I give the second or my original or my input. Few shots prompt as the same. We have here the instruct, first example, and second example. Okay, let's highlight also what we call chain of thought prompt. So you can see here in this example, we have an instruction, but an instruction about some reasoning of mathematics. Okay, so Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis holes does he have now? This is very difficult for an LLM. Why? Because it is based on what? On generating text. That's why LLMs aren't good at mathematics. They just generate next word. Okay, so here we give, for example, the answer is 11. This is a prompt with is one short prompt example, and the second then now is the second prompt, or my prompt is the cafeteria has 23 apples if they use and so on. So the question, how many apples do they have? Model, it answered with 27. It is wrong. Okay, but we know why. Because the LLM doesn't do any math. This instruction or this prompt needs more mathematical reasoning. So chain of thought prompting argues that we can give here an example with some reasoning in mathematics, like here. So this is the same prompt, but as the answer, I don't give here just the answer, I give a reasoning step by step. Roger started with 5 volts, 2 cans of 13 volts, each is 16 volts, 5 plus 6 equals 11. The answer is 11. Now, if I give the same prompt to our LLM, you can see here that the completion is also formatted as a reasoning, and then the answer is correct. That's why prompt engineering is still in demand. Okay, so this is just this is also very, very important. This is always an emergent ability. So you can replace this logical reasoning by just, right, let's think step by step. So instead of giving an example with reasoning, we can replace this with just, let's think step by step. Okay. Maybe in some applications, zero shot, one shot, and few shot prompts can work better. And in this case, you should fine-tune your LLM. And fine-tuning involves updating the weights of your pre-training. Okay, instead of in-context learning, we don't update the weights. Here, when we fine-tune our model, so we have to update the weights. Also, OpenAI API takes the developer, the engineer at ease, okay? And it's surprising. You can fine-tune your the GPT using just the script. You use the fine-tuning API endpoint, job create. So training file, so you should upload your training dataset before using another endpoint called files, and then you can here set the hyperparameters and epochs. So before we have just an epoch, the one parameter of the single file, the unique parameter that we can set here when fine-tuning. But now, so maybe in November, we have OpenAI have added 2 other parameters. So the alpha learning or the learning rate. Okay, so you can see here it is code to start fine-tuning easy. LLM use cases, so real-world applications. So there are many applications. So all the NLPs are tasked to know language translation questions, read chatbots, and so on. And also you can develop some LLMs powered application. So there are applications powered by LLM. So here we know that some or LLMs have some limitations, like for example, the internal knowledge held by a model cuts off at the moment of pre-training. So here, for example, GPT-3, so the knowledge of the data set used for pre-training is up to 2021. GPT-4 is up to April 2023. So if, for example, we prompt GPT-3 to maybe answer what is the maybe the head coach of the Morocco national team, can't respond accurately here. Because before 2021, we have Khalid Hadouzic, but now we have another one. That's why LLMs hallucinate and so on. So we have also another problem, struggling with complex math. So based on the text generation, it is very difficult to imagine a model that can respond accurately to mathematical reasoning. Okay, that's why we have now what we call retrieval augmented generation. So it is a framework that we can use in order to augment our LLM by accessing to external data sources. And also, maybe if we have a prompt that includes mathematical reasoning, we can, for example, interact with a Python interpreter in order to give or to return the correct answer and then interact with the LLM. So LLM-powered applications are very interesting. So you can see here some of those applications like Bing Chat. So here your question is, who is Colombia's current president? So Bing performs at first search engine or an information retrieval system here. The top search results are extracted. Then they pass to they add to the prompt or to the first query, and these results plus this query constitutes or what we call the new prompt that will be passed to our LLM. Another example about this in enterprise knowledge plus LLM equals intelligence bot. So you can see here that the consumer, for example, wonder what are various options for me to get home loan. So the LLM can't answer to this question because it is related to what? To the enterprise knowledge repository. And in this case, what we can say, we can add here a retrieval relevant context from the enterprise knowledge discovery, and then add this relevant context to the user query in order to create what we call a prompt, and then the LLM can answer and chat with the user. It is okay. So you can also use LLMs for embeddings, okay, but with another objective. Okay, so the new paradigm of AI now. So currently, if you have a project in your enterprise, so you can start with classical coding to help build the AI pipelines and so on, expert systems, then classical machine learning algorithms, then next classical deep learning tasks, then partially trained transformer models that can do one or more few tasks, and finally, you can opt for foundation models. Okay, so that can do NLP tasks, computer vision, and work with one model. So LLMs are a subset of foundation models, just to mention. So if you opt for the last choice, which is use an LLM foundation model, so this is a generative AI lifecycle project. So we can choose the final use case, select an existing model, then adapt and align your model by prompt engineering, fine-tuning, and so on, optimize and augment. Okay, this is the last slide about challenges and some future directions. So transformer complexity. So currently, so the transformer has a great limitation about the complexity time. So it is a quadratic complexity time. That's why now we so some emergent architectures are based on what we call the performer, okay, and retention networks and so on. So a performer is just approximate the software description used by the attention mechanism by a product of multiple matrices. Emergent abilities, we don't know, for example, one and how they are obtained by an LLM, like in context learning, so few shots and so on. So there are many efforts on this. So some mathematical models and so on try to demystify and to explain this. And so existing prompting approach and the reinforcement learning from human feedback. Heavily, it relies on high quality human feedback from professional levels.